Welcome everyone. In this video, we can discuss about one error detection and correction technique, that is about the Hamming code. In our previous video, we have discussed about this parity code and checksum. And for the explanation of this cyclic redundancy check, we need to know some additional operation that will explain sometimes later in the subject. So after that, we can consider this cyclic redundancy check mechanism. So now we can directly move to this Hamming code. So this is some basic idea about the Hamming code. Hamming code is a block of code that is capable of detecting up to two simultaneous bit errors, and it can correct a single bit error. Okay, that means Hamming code is used for both detecting and correcting errors. It can detect up to 2 bits errors and can correct single bit error present in the transmitted data. It was developed by R.W. Hamming and is for error correction. So the basic part of this Hamming code is certain redundant bits. These are the extra binary bits that are generated and added to the information or added with the data to be transmitted to ensure that no bits were lost during the data transfer. So the important part of this Hamming code mechanism is certain redundant bits that these bits are added with the data to be transmitted. This will ensure that no bits were lost during data transmission. So here we have different steps for performing data encoding. That means the procedure used by the sender to encode the message encompasses the following steps. What are the steps? Calculation of the number of redundant bits. Then positioning the redundant bits. Calculating the values of each redundant bits. So before transmitting data in the scheme, we need to identify how many redundant bits are needed for the proper working of this system. After identifying or after deriving the number of redundant bits required, we need to fix the position of each and every redundant bits. After that, we need to calculate the value of each and every redundant bit. This procedure becomes more clear with certain example. Okay, so the first step, number of redundant bits that can be calculated using a formula, that is this: 2 to the power r is greater than or equal to m plus r plus 1, where this r is number of redundant bits and this m indicate number of bits present in the data to be transmitted. So keep this formula in your mind. So using this, we need to fix the value of r. Thus, r indicate the number of redundant bits that are needed for transmitting a data that contains m bits, m data bits. Okay, so using this formula, suppose the situation is like this. We want to transfer a data with 7 bits. Now we need to fix the number of redundant bits required. So using this formula, start with the value of 1 for this r. If r equal to 1, then this term, LHS term become 2 to the power 1, that is 2. And this RHS, m plus r plus 1 means 7 plus 1 plus 1 is 9. So here this 2 is less than 9. This is not satisfying this given equation. So for the value 1 for this r, this is not valid here. For transmitting 7 bit of data, we need some other value for this r. So consider r with value 2 now. In this case, this part become 2 to the power 2 as 4, and here it become m plus r plus 1. That is 7 as the number of data bit to be transmitted, plus this r value, that is 2 plus 1 equal to 10. Here again 4 is less than 10. This is not valid case of this formula. So we need to consider another value for this r. Now we take 3 for r. So 2 to the power 3 is 8. M plus r plus 1 becomes 7 plus 3 plus 1 is 11. Again 8 is less than 9. For this r equal to 3, again this formula is not valid. So go for r equal to 4 now. Here 2 to the power 4 is 16. And here m plus r plus 1 becomes 7 plus 4 plus 1 is 12. Now this 16 become greater than 12. The condition is satisfied here for the value of 4 to this r. So now we can fix the number of redundant bits required for transmitting a data of 7 bits is 4 now. Okay, so using this formula, we can decide the number of redundant bits required for transmitting a given m bit data. Here it is 4 for transmitting a data of 7 bits. Okay, the second step is positioning the redundant bits. We have In the first step, we have identified or derived the number of redundant bits required for transmitting a data of m bits. After that, we need to decide where to place these redundant bits along with the data. Okay, so usually the redundant bits, generally we can represent this as R. The R redundant bits placed at bit position of power of 2. That is at 2 to the power 0, at 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4 and so on. So we can place the redundant bits at position 1, 2, 4, 8, 16, etc. In our previous example, we need to place 4 redundant bits for transmitting a data of 7 bits. In that case, along with the data, we need to place the 4 redundant bits at position 1, 2, 4, 8, 16, etc. Okay. So consider the case. For transmitting 7-bit data, at place 1, we need to place a redundant bit. This redundant bit can also be called as the parity bit. Okay, so we can write here a redundant bit. The first redundant bit or the parity bit can be placed at position 1. And in the second power of 2, that is 2 to the power 1, here we can place the second parity bit. And at third position, this 3 is not a power of 2. So here we can place the least bit of our data to be transmitted. And at position 4, 4 is a power of 2, and here we can place a redundant bit or the parity bit. And 5, 6, 7, these are not the power of 2. So these places are used for storing data bits. And 8, this is 2 to the power 3, a power of 2. So here this place we can use for storing parity or redundant bit. 9, 10, 11, 12, 13, 14, 15 are not power of 2. So here we can place data bits. And at 16 we can place parity because 16 is 2 to the power 4, a power of 2. Okay, so this is the second step. Identify the position where to place the redundant or this parity bits like this. Okay. The third step, calculating the values of each redundant bit. This is the third and final step, calculating the values of each redundant bit. This P, this, etc. The redundant bits are actually parity bits. Okay, this parity is an extra bit that make the number of ones either even or odd depending upon the type of parity system we are following. That means we have different parity system like even parity and odd parity. So based on the type of parity system we are following, we need to make the value of this parity bit either 0 or 1. Exactly like the principle that we have discussed in case of parity code. Okay, so These are the rule for setting different parity bits. For setting parity bit 1, for setting a value for parity bit 1 covers all the bit position whose binary representation includes a 1 in the least significant position. Right? Consider this. So for setting a value, a correct value for this particular parity bit, we need to consider different positions, the binary representation of different position, and we need to consider the position in which the binary representation contains the least position with a value 1. So these are the positions that contains least position with value 1, like this 1, 3, 5, 7, 9, etc. So here for this 1, the binary representation is this. The least bit contain a 1. And for 3, the least bit contains 1. And for 5, the least position contains value 1. And for 7, the least position contains value 1. And for 9, the least bit is 1. Similarly, for parity bit 2, for this particular parity bit, for setting a proper value for this parity bit, we need to focus on the second least significant bit of each and every position. If there exists a value 1 in the second least significant bit of the positions, then we need to consider that values present to that corresponding locations. Here, for setting the parity bit 2's value, we need to consider positions like this 2, 3, 6, 7, 10, etc. Why? Because for this 2, the second least significant bit position contains value 1. Here for this 3, the second least significant position contains value 1. And for 6, 7, and 10, here the second bit position, second least significant bit position contains value 1. Okay, so we need to consider the value present at these positions for setting the parity bit 2's value. And for similarly, for setting value for parity bit 4, we need to cover all the positions that whose binary representation includes a 1 in the third position from the least significant bit. So for the numbers, for the positions 4, 5, 6, 7, etc., the least significant third position contains value 1. For the 4, the representation is like 0, 1, 0, 0. The least third bit position contains a value 1. And for this 5, this is 0, 1, 0, 1. The least third bit position contains value 1. And for 6 and 7 also, the least third bit position contains value 1. So for setting a proper value for parity bit 4, we need to consider the value present at positions like this 4, 5, 6, 7, etc. And for setting a proper value for the parity bit 8, parity bit 8, okay, we need to consider all the position whose binary representation includes a 1 in the fourth position from the least significant bit. Okay, so fourth position from least significant bits equal to 1 for the positions like 8, 9, 10, 11, 12, etc. Okay, 8 means 1, 0, 0, 0. The fourth least significant bit is 1. And for this 9, the binary is 1, 0, 0, 1. That means the least fourth bit of this binary is 1. And for 10, the binary is 1010. The least fourth bit of this 10th binary is 1. Okay, so all these positions we need to consider for setting a value for this parity bit 8. and for follow this same principle for the remaining parity bits also. Okay, so here we can consider one example. Okay, so after this explanation, the mechanism become easy for you. Okay, this is the data, a 7-bit data that we want to send. The number of bits present in this data is 7. So for uh, sending this 7-bit data, how many redundant bits or parity bits are required? We have already derived this. For sending 7-bit, we need 4 redundant bits. That is derived using the formula 2 to the power r greater than or equal to m plus r plus 1. So here we derived that number of redundant bits required is equal to 4. So total size of the data to be sent now is 7 plus 4, 11. Total number of bits to be transmitted, 7 data bit with 4 parity bit. Total 11 bits. The redundant bits are placed at position corresponding to power of 2. Okay, like this. So here for sending this data of 7 bits at position 2 to the power 0, that is 1, we can place the first parity bit. And this is 2 to the power 1. This is 2 to the power 0. This is 2 to the power 1. Here we can place the second parity bit. This is not a power of 2. So here we can place the first bit, the least bit of our data. That is 1. Again, it is a power of 2. Here we can place the next parity or redundant bit, that is P4. Okay, and these three are not a power of 2. So here we can place this 0 here, this 0 here, and this one here. Again, here we can place the fourth and last redundant bit required here. And here we can place the next bit of our data, this 0 here and this 1 here. So this is the data or full sequence of data that we are going to transmit after appending the redundant bits along with the data. Right. After this, we need to identify these values for these parity bits. Okay. So these are the positional values of each and every bits. For this P1, for setting a proper value for P1, we need to consider all the positions. Its binary representation contains the value 1 at its least position. Right? So these are the such position. This one, this one, this one, this one, and this one here. Means position 3, 5, 7, 9, and 11. In these position, the binary representation of this position with least significant bit value equal to 1. Okay, these values, the values present at these locations are required for setting the parity bit P1. Okay, 3, 5, 7, 9, and 11. So here consider the value present at these locations. At 3, the value is 1, and at 5, value 0, 7 with value 1, 9 with value 1, and 11 with value 1. That means how many ones? Here we are going to follow even parity system. Even parity system. That means here we can set value equal to 0 if these position contains number of ones equal to an even number. If this particular position hold a value equal to 1 if these position contains ones, the number of ones present at these locations is equal to an odd number. In that case, in order to make this an even number, we can set a value 1 here. If these positions together contains odd number of ones, then here we need to set value 1. If these positions together contains even number of ones, then we can set value 0 here. Okay, this is the rule of even parity system. Generally, we are following even parity system along with this Hamming code. Okay, so consider these bit positions and the value. So total how many ones? Here we have 1, here, here and here. Total 4 ones. Okay, 4 ones is an even number. So we can set the value of P1 as 0. Total 4 ones are present together in these locations, right? So we can set value 0 for this P1. Okay, so this is the current status. After setting value for P1, here we have 0 now. Okay, consider the second case. Now we can set the value of P2. For setting the value of P2, which positions we need to consider? All the position whose binary representation contains the second least significant position with value 1. So what are they? This one, this is the position of our second parity bit. So we need to set a value here. So remaining such positions are this 3, this 6, 7, 10 and 11. 3, 6, 7, 10 and 11. Now we can consider the value present at these locations. 3 with value 1, 6 with 0, 7 with 1, 10 with 0, 11 with 1. Okay, so here in these positions, consider the ones present in these position. It is an odd number. We are following even parity system. So in order to make an even number, we can set this P2 with a value 1. Here we have 1 and next here we have 1, second one, and here we have the third one. Total 3 ones in these positions. 3 is an odd number. In order to make it an even number, we can set a value 1 for this parity P2. Okay, so this is the case. After setting value for P2, here comes value 1. Okay, next we are going to set value for our next parity bit, that is this P4. For setting value for this P4, we need to consider the position whose binary representation contains 1 in its third least significant position. So what are the position? Here we have third bit, third least significant bit with value 1. Here also, here also. Okay, so we need to consider the value present at 5, 6 and 7. 5 with value 0, 6 with value 0 and 7 with value 1. Okay, so here total number of ones in these bit positions or in these locations is odd number. In order to make it an even number, we need to set here for this P4 a value 1. Okay, so this is the status after setting value for this third redundant bit. Okay, and for this P8, that is the fourth redundant bit. For setting a proper value for this particular redundant bit, we need to consider all the position with the uh, the fourth least significant bit position with value 1. Okay, so what are the locations? This 9, 10 and 11 here. We need to set a value here at location 8. We need to focus on the values present at location 9, 10, 11. Here the fourth least bit position having value 1. So here at 9 we have 1 and here also 1. That means total 2 ones here in these 3 locations. 2 is an even number. Okay, so already even number of ones are present here. So P8, this particular redundant bit is set with a value 0. So this is the current status of our data to be transmitted. So after setting proper value for 4 redundant bits, now this is the data to be transmitted. Okay, the data is going to transmit us this 11-bit information after adding 4 different parity bits. Okay, so at receiver side, suppose this data is received without any error. The same data is received at the receiver side without any error. So consider this is the situation. So in that case, what we want to do at the receiver side, we need to consider the locations for this P1. That means the location with least significant bit with position least significant bit position with value 1. What are they? P1, P3, P5. Sorry, the positions 1, 3, 5, 7, 9 and 11. In all these positions, in its binary representation, we can see the least significant bit contains value 1. So now consider the value present at these locations. Here we have value 0 and here at position 3 we have value 1. And at position 5 we have value 0 and at position 7 we have value 1 and at 9 we have 1 and at 11 we have 1. Now consider or count number of ones present here. 1 plus 1 plus 1 plus 1, total 4 ones, means even number of ones. So we can set a value with 0 because here it present even number of ones in these positions. So this P1 dash is set as 0. Similarly for this P2, consider next case. Next is the values present at locations whose binary representation contains 1 at second least significant bit position. So what are the location? This 2, 3, 6, 7, 10 and 11. In all these position and its binary representation contains second least bit position with value 1. Now we can consider the value present at these positions. Here it is 1, here it is again 1, here it is 0 and here it is 1 and here it is 0 and here it is 1. Now count the number of ones present here. 1 plus 1 plus 1 plus 1, 4 number of ones. Okay, 4 means an even number. So we can set this P2 dash with value 0 because here it already present even number of ones. So we can set P2 dash as 0. And for this next case, here this is the third redundant bit. For this particular position, we need to consider these other positions 4, 5, 6, 7 because in all these cases the the third least bit position of its binary representation contains value 1. 4, 5, 6 and 7 here. So here at position 4 here it is value 1 and at 5 here it is value 0 and at 6 value 0 and at 7 value 1. So total 2 number of ones. 2 is even. So we can set this P4 dash as 0. And now we can consider this P8. P8 means the fourth redundant bit. For setting P8 dash, we need to consider different positional values whose binary representation contains a 1 at its least fourth bit position. Least fourth bit position. That is this 8th position, 9th position, 10th and 11th position. Here we have 0 and for 9 we have 1 and for 10 we have 0 and for 11 we have 1. Here again 2 number of ones. 2 is an even number, so this P8 dash is set as 0. Now we can arrange this P1 dash, P2 dash, P4 dash, P8 dash like this. P8 dash, P4 dash, P2 dash, P1. Its value is 0, 0, 0, 0. So at receiver side, after evaluating or counting number of ones at each and every positions like this, If this representation is like this, that is full of zeros, then it indicates that after transmission, no error occurred to the data. If it is full of zero after deriving these values, that means we can conclude that here the received data is exactly matching with the transmitted data. That means no error occurred to the transmitted data. Okay. Then now we can consider some other example that indicating certain error that occurred during transmission. Okay, so this is the actual data sent by the sender. But during transmission, here at position 6, actual data is 0, but during transmission, its value gets changed to 1. So this is a case of error. So at receiver side, this is the data which is received at receiver side. Now we can follow the same procedure. For P1 dash, we need to consider all these positions. And here we have value 0, 1, 0, 1, 1 and 1. Now count how many ones are present here. 1, 2, 3 and 4. So even number of ones present. So P1 dash is set as 0. Now for this P2 dash, which positions we need to consider? All the position whose binary representation contains ones in its second least significant bit position. Such positions are 2, 3, 6, 7, 10 and 11. So these are the positions we need to consider for setting P2 dash. Okay, so here value 1, here again 1, and here we have 1, and here we have 1, and here again 1. So now count number of ones present here. 1, 2, 3, 4, 5. 5 is an odd number. Okay, so in order to make the entire system 0, we can set this P2 dash as 1. Okay, if it is odd number, then P2 dash is set with value 1. If it is even number, then that parity bit, corresponding bit position, parity or redundant bit position is set with value 0. Okay, next this particular, we need to calculate P4 dash. Okay, so for that we need to consider the location 4, 5, 6 and 7. For 4 we have value 1, here 0, here 1, 1. How many ones present? 3 ones. That means an odd number. Again we need to set value 1. If it contains odd number of ones, then set the value 1. If it contains even number of ones, then set here with value 0. Again, this one. For this, we need to consider positions like 8, 9, 10 and 11. These are the positions that contains a 1 in its fourth least significant position. Okay, so here we have 0, here 1, here 0, here 1. So total 2 number of ones. 2 is even. So we can set value 0. Then arrange like this: P8 dash, P4 dash, P2 dash and P1 dash. So the value is like this: 0, 1, 1, 0. This 0, 1, 1, 0 is the binary representation of decimal 6. From this, we can conclude that at position 6, we had an error. So this particular value indicate the position that contains an error. So 0110 indicates the binary of decimal 6. From this it clear that we had an error at position 6. So we need to correct it. How to correct? Flip the value currently present at position 6. At position 6 it contains 1. So we need to change the value from 1 to 0. So this is the correction. So this is the detection. We detect here an error at position 6. And this is the mechanism of correction. We need to flip the value at position 6. Whatever value present at location 6, we need to flip it. Here it is 1, so we need to change that 1 to 0. Okay, consider one more example. At ninth position, actual data contain value 1. So while transmission, there occurred certain error. So this value get changed to 0 here. So at receiver side, this is the data which is received at receiver side. So the receiver data contains an error at location 9. So the same procedure for this. Consider the values present at this location. Here contains value 0, 1, 0, 1, 0, 1. Total 3 number of ones. 3 is odd. So P1 dash is set with value 1. And for next parity bit, we need to consider the values present at these locations. Here contains even number of ones. So P2 dash is set with value 0. And for next redundant bit, we need to consider the value present at these location. Here it is even number of ones. Okay, so we can directly set with value 0 here. And again here at for this P8, we need to consider location 8, 9, 10 and 11. Here it contains only a single one. This one is an odd number. So make this P8 dash with value 1 and arrange this like P8 dash, P4 dash, P2 dash, P1 dash. So the value is 1001. 1001 is the binary of decimal 9. This indicates that while transmission, an error occurred at location 9. So for correction, we need to flip the value present at location 9. So here it contains value 0, so we need to flip it. Here it is 0, we need to correct it by changing the value from 0 to 1. Okay, so this is the method of error detection and correction using Hamming code. Okay, thank you.